All right, guys. We're going to look at a very different looking static equilibrium problem than the one that we did in class. This one is a little bit harder. It has a couple more variables in it. We're going to solve this a couple different ways. So you'll see, in different parts of this video that I'm just going to resolve the problem at least two different ways and with a couple different axes of rotation just to prove that we can. So we have a ladder, and this ladder is leaning against the wall. So there's going to be two contact points, one at the floor and one at the wall. They told us that the coefficient of static friction of the wall is 0.3 and the coefficient of static friction of the floor is 0.4. They told us that the center of mass of the ladder is right in the middle, which is good. And what they want us to do is find the minimum angle that this thing can be leaned at before it starts to fall, before it starts to slip and slide down and hit the ground. So the first thing we should do is draw a picture of our system, and then we're going to label the forces acting on it. So I'll have a picture drawn right now. All right, so I've drawn the picture. We see down here near the bottom, the ground. Over here, we've got the wall. The brown thing leaning is the ladder. This is like a side view. I've labeled our coefficients of friction as U static W for the coefficient of static friction for the wall, and U static F for the coefficient of static friction for the floor. I've also labeled over here our angle. This is the angle that we're going to look for, the minimum angle that this thing needs to be at, the smallest angle I could make this, right? The closest to the ground I can be before this thing is going to slip. One thing that they didn't necessarily tell us, but that I've also labeled, is this length L. That's the full length of the ladder. I've also identified right here in red the middle point, the center of gravity of the ladder. And this is going to be really, really important. Now on this picture, we're going to draw all of the forces that are acting on my system, on my ladder. This is going to be useful for two things. Number one, this will be really useful for solving the sum of forces equations, because, we need our free body diagram to write out a sum of forces. And number two, it'll be really useful in our sum of torques equations so that we can figure out where our forces are, and we'll be able to figure out our lever arms to our axes of rotation. Speaking of, we actually haven't identified an axis of rotation yet, and we're not going to until we get to the torque part, so don't worry about that yet. The red dot is not the axis of rotation, it is the center of mass. I just wanted to identify that. All right, so let's start drawing our forces. I'm going to draw them in a thick purple color. We know that forces come from two places, fields, and the only field that we know is the gravity field, and the gravity force is going to act on my object from the middle, and it's going to pull this thing down. So I'll call that FG to make our lives easy. And the second place that forces come from are contacts. So there are two major contact places, right here at the wall and right here at the floor. I'm going to start with the floor. Well, the floor is applying a normal force on this ladder. It's preventing it from falling down and sinking, right? So it's going to apply a force upwards. And I'm going to label that the normal force from the floor You could call it FNF if you'd like. I'm just going to call it N for normal. But it's also applying a friction force that's stopping this ladder from sliding. If there was no friction, this system would slide, or at least the ladder would slide that way, right? To the left, which means if I have a friction force, it's going to oppose the motion. It'll go in the opposite direction of motion. So my friction force here should go to the right. And I'm going to label that my curly F for friction, F for floor, subscript F for floor. All right, my other contact point is over here at the wall. And that's also going to produce a normal force perpendicular to the wall. So that's going to go that way. Now, I don't want you to get caught up on the lengths of my arrows. They're meaningless right now. I'm just drawing arrows. Just because this one is smaller than this one doesn't mean that this is a smaller force. I'm just drawing arrows. I'm not an artist. I'm sorry, guys. I'm going to call this one NW for the normal force of the wall. The wall is also providing a friction force. If there was no friction, this point of the ladder would actually slide down that way, right? Which means that friction will oppose that, and it's going to keep it by pushing up. And I'll call that my curly F for friction, W for wall, FW. All right, there are no other contact points. There are no other fields, so there are no other forces. That's it. Those are all of the forces that we have. This is a little bit more complicated than the other pictures that we've seen, but that's okay. One really nice thing, though, is that all of our forces are one-dimensional. We've got a bunch of perfectly vertical and a bunch of perfectly horizontal forces, so at the very least, we don't have to worry about components yet, which is really, really good. Okay, so what I'm going to do, just because I know that if this system is in static equilibrium, it needs to satisfy the first condition of sum of forces equals 0. So I'm going to write out my sum of forces equation over on the right-hand side. Because I've got two dimensions, the x and the y, I'm going to end up having two sums of forces. So I'm going to start with, let's start with the y. I'm going to write these over here on the right-hand side. So the sum of forces in the y, I have 1, 2, 3 forces that are in the y. So I will have 3 terms in my sum of forces. So that will be, whoop, wrong color. We're experiencing some technical difficulties. There we go, back to purple. That will be my friction from the wall, which goes up, so that will be positive, plus my normal force from the floor, which goes up, so that will be positive, plus my negative gravity, that's going down. And this should be 0. I don't want my system to move. Now, I don't know what the mass of this thing is, so I don't know Fg. And I don't know normal force, and I don't know friction force. So we've got a bunch of unknowns in this one. I'm going to write my sum of forces in the x direction. Okay. And I have 1, 2 forces in the x direction, my friction force from the floor and my normal force from the wall. So I should have 2 terms in my sum of forces. My friction force from the floor is positive because it points to the right, plus my negative because it points to the left, normal force from the wall, and that will equal 0. So I've got these 2 sums. Unfortunately, they're full of unknowns, so that's going to be pretty difficult for us. That's okay. You're going to see that this is all going to work out really nicely. Unfortunately, there's not a lot of numbers, which might be uncomfortable for some of us, but this is why we're going to take it slow. It's all going to work out in the end. Now, the thing that they want us to solve for is theta. And if we've noticed, we should have been paying attention to our sums, the force sum actually doesn't have any theta terms in it. All of my forces here are one-dimensional. So there's a really good chance that I'm not going to use just my sum of forces to solve. Thankfully, we have a second condition, our sum of torques condition, and this condition will end up having an angle term in it, because if we remember, the equation for torque is rf sine theta, which is good because that means it actually has an angle piece in it. Now, the angle piece doesn't have to be that theta. If we remember, this theta connects our lever arm R with our force F. It's the angle between those two. But if we're clever and we draw our lever arms and we pick a good axis point, we can, using geometry, find expressions for this theta that's in our equation for torque and turn it into this theta, which is what we want to find, the angle, the minimum angle. Okay, now we're going to solve this problem two major different ways. The first way is going to be with torques using this equation, rf sine theta, and then taking advantage of a little bit of geometry to figure out what these expressions are going to be with our angle. The second way that we're going to solve is by taking advantage of the line of action and finding perpendicular distances so that we don't have to use this sine theta piece and make our lives easy. We're going to do the line of action part second. That's going to be later on in the video. The way we're going to solve right now is by using this equation, rf sine theta, and by drawing our lever arms and taking advantage of a little bit of geometry. So I've redrawn the picture. I've gotten rid of the force stuff because I'm going to look at the torques. We've already established that those force equations aren't really going to give us what we want to use because there's just too many unknowns. If I combine those, if I couple them with some torque equations, I could do some substitution and figure out all of my unknowns, or at the very least figure out my angle, which is what I want to find. So I'm going to start looking at my torques. But we know that if we're going to solve for torques, I need to pick or establish a lever arm. Without a lever, I mean an axis of rotation. Without an axis of rotation, I can't find lever arms because the lever arm always goes from the axis to the force. Now we can pick any point that we want to be our axis of rotation, because if any one point would produce a system in static equilibrium, then all points would produce a system that's in static equilibrium in this case, in all cases that are static actually. Now we saw in class that we could pick nice places and some not so nice places. I'll get the same answer no matter what place I pick. The biggest difference will be how many terms I'll have left over and what types of terms, so whether or not I have knowns or unknowns. Now I am going to pick a slightly controversial point to be my axis of rotation because I already know that I'm missing one major variable, and in order to make my life easy, I'm going to get rid of it. So the variable that I'm definitely missing that's pretty huge for us is the mass of the ladder. So the variable that would help us find this FG. And that's a problem. So what I'm going to do is I'm going to pick that point to be my axis of rotation so that I could eliminate that FG force from being a thing. Now, I don't have to do that. What I could do is pick any one of the other two interface points, either the one on the floor and the one on the wall. And the nice thing that would do is eliminate two forces instead of one, but I would still have the problem of having this FG be unknown. I could solve that problem by doing some clever substitutions with my sum of forces and my torques, but I'd rather just kind of get rid of that situation altogether and not have to worry about it at all. So that's the way that we're going to go. This center point, I'm going to highlight it in green. Actually, I think this is going to be way too thick, so I'm going to highlight it like this in green. This center point right here is now going to be... Why did that do that? Well, okay. Let's... Oh, that's not what I want to do either. So, how about black? Okay, that looked like it stuck. Well, that center point right there will be my axis of rotation. I'll call it my AOR. Now that we've established an axis of rotation, we can start writing out our sum of torque equations. All right, so I'm going to write them in black over here on the side, and I could say that the sum of my torques around my axis of rotation, let's give it a I'm going to call this A just to make my life easy. So my sum of torques around A is going to equal, well, I have already established that FG isn't going to produce any torque because it's going to go through that axis of rotation. So that leaves me with the normal force from the floor, the friction force from the floor, the normal force from the wall, and the friction force from the wall, all producing torques. So I'm going to start off with our positive torques and then end off with our negative torques. So remember that counterclockwise torques are positive. This normal force from the wall is going to rotate my ladder counterclockwise. So that's going to be a positive torque. So that will be the torque from the normal force of the wall. This friction force from the wall will also rotate my system counterclockwise relative to this axis of rotation. So that will also be positive. So plus the torque from the friction force of the wall. Now, the normal force from the floor is going to rotate my system clockwise, so that will be a negative torque from the normal force of the floor. And my friction force from the floor down here will produce a negative torque. It will rotate this system. Nope, actually, I am a liar. I'm sorry, I misspoke. This friction force will cause my system to rotate clockwise. Yep, I'm sorry, guys. I'm feeling a little slow. Counterclockwise. Wow, I misspoke. I'm all over the place. Okay, so this friction force is going to rotate my system counterclockwise. So that'll be a positive torque from the friction force of the floor. And if this system is all going to be at static equilibrium, it should equal 0. Now what I can do is substitute in what we know torque is. We know that torque, tau, is the lever arm times the force times sine of the angle between them. So I can apply this definition to every single one of my expressions in my sum for torque. And what I'll start with this one. So the torque caused by my normal force from the wall is going to be my lever arm that goes from my axis to my normal force of the wall times my normal force of the wall times sine of the angle between them. So what does that look like? Well, the lever arm is going to go from my axis of rotation here, and I'm going to draw this as a much thicker line. So my axis of rotation here, all the way to where my force is applied. It'll look like this. That will be my lever arm towards NW. What's going to be my angle between the two? Well, here is my force NW, my force normal from the wall. Here is my axis of rotation, my lever arm, right? And the angle will be right here. Now, the nice thing about this angle is that this force normal is parallel with the ground. And this line is a bisector. So this angle right here is actually equal to the angle that we're looking for, theta, here in the bottom in pink. They are alternating interior angles, which is good because that means if I could solve for this theta, I could solve for the angle that I'm looking for. This is a good thing. The next thing I need to worry about is what is my lever arm? Well, I know that my axis of rotation is in the middle of the ladder, and my lever arm is pointing from the middle of the ladder all the way to the end of the ladder. And if my ladder has a length of L, then my lever arm is going to be L over 2. So I could rewrite this as, I'll keep it like this actually. I could rewrite this as L over 2 times the normal force from the wall times sine of theta. Okay, and all of this would be that first torque term. All right, what I'm going to do is solve for the next torque term, and I'm going to do that in a different color, and I'm going to color coordinate each one of these, and then I'm going to write one big fat sum. So the next one is going to be in blue, and that's going to be this torque term right here. I'm going to write it right above. It's going to look a little bit confusing, bear with me. I don't have a huge amount of space. Now that's going to be the lever arm towards the friction force of the wall times the magnitude of the friction force from the wall times sine of the angle between the friction force and the lever arm. You know what? Let's change that. Instead of being a theta, because that can be very confusing, I'm just going to call it a different variable for angle phi, just to make our lives easy. I don't want us to get confused between the angle that's in our sine theta for our torque and the angle theta that we're solving for, which is in our picture. So I'm just going to call it a different variable. Now, let's draw our lever arm for this force. That's going to go from, again, my axis of rotation to my force, Fw, and that's going to go from here, which is my axis of rotation, and it's going to point right over here. Technically, it's supposed to be right on top of the red line, but I'm trying to show that, these different vectors are pointing in the same direction, and they don't disappear. Okay, well, using the same argument that I made for the lever arm of the normal force from the wall, I can see that the lever arm for the force of the friction from the wall will also be L over 2, because it's half the length of the ladder, times the force of friction from the wall times, now we have to be a little bit tricky, because the angle is going to go from my lever arm to my force. That's going to be a little bit bigger than the theta that we're looking at. In fact, it's actually going to equal the same theta from our previous torque, which is the answer that we want, plus 90 degrees, this extra 90 degrees piece right there. So I could write this as sine of the theta that I actually want, which was right here, that red theta that we had in the last torque term, plus 90 degrees from this perpendicular component here between our normal force and the friction force of the wall. And this whole term is going to represent that torque there. Okay, we've got 2 more torques to go. I'll do this next one in green. So this torque right here, I'm going to draw or write out over there. So the torque from the normal force of the floor is going to equal the lever arm or from the axis to the normal force of the floor times the normal force of the floor times sine, and again, I'm going to use a different angle. I'm not going to say theta because I don't want to get confused. I'll call it phi again. That's fine. Just a different angle. It's the angle specifically between the lever arm and the force. Well, the lever arm is going to point from my axis to my force vector down here at the bottom by the floor. So it's actually going to look like this. I'll label that R and F. Oh, I actually didn't label our last lever arm, so I'll go ahead and label that R friction W. Okay. And I can see really quickly, again, if my lever arm goes from the center of my ladder to the end of my ladder, that's going to end up being magnitude L over 2 times the magnitude NF times sine of, now we got to pick our angle again, and this time it's going to be this angle right here. That's our angle phi that we're looking for. But I can do some pretty tricky, some very good, nice geometry, and I could redescribe the angle phi in terms of the theta that I'm looking for. That's really what I want to do. I want to make sure that anywhere that I have an angle, it's the angle that I'm looking for. I don't want to mix my angles because then it's going to make it impossible for me to solve for my theta. So I know that my angle phi plus my angle theta is going to equal 90 degrees. I know that because right here in this corner, this is a right triangle, or a right angle, I'm sorry. What that means is I could redescribe the angle phi, which is the angle between my force vector and my lever arm, in terms of theta and a constant, my constant number 90, which is good. All I would need to do is subtract theta from here, move it to the other side, and that would end up giving me 90 degrees minus theta. So one thing I definitely want you to keep track of in your head, if you notice, here my angle, my variable is theta. Here my angle, my variable is theta. Here my angle, my variable is theta. So far, in 3 of the 4 terms that we've written out, our variable in our angle is theta, which is good. I'm looking to solve for theta. Now I do have some ugly stuff, you know, a 90 minus theta over here and 90 plus theta over here, but that's okay. We're going to take advantage of some trigonometry and some geometry, and we're going to get rid of those. All right, I've got one last term to find. I'm going to do that term in purple. Okay, that would be this guy right here. Now that guy, the lever arm is going to point just like the last one. It's going to point from the axis down to where my force is, that would be R friction floor, okay? So the torque from the friction floor would be equal to the lever arm R for friction floor times the force friction floor times sine of the angle between them. Again, I'm not calling it theta, I'm calling it phi, just a different angle. Well, I think by this point you guys already have a pretty good idea of what that lever arm is going to be. It's still starting from the middle, it's still going all the way to the end, so it's still going to be L over 2 times the force of friction from the floor times, now, where is my lever arm? And if you look at the picture, you'll see that, not my lever arm, I'm sorry, my angle. If you look at the picture, you'll see that our angle is going to be this angle right here, which is theta. It's the variable that we're looking for. So I can write this as sine of theta. And again, for our last term, we'll notice that our variable for angle is exactly the angle that we're looking for. It is theta. It's not some other weird angle. So now that we've got these 4 expressions for our theta, what we're going to do is rewrite them in a much prettier way. This is very, very messy. So I'm just going to spend a little bit of time rewriting them, and then I'm going to isolate my variables. All right, so what I've done is I've rewritten our expression for our sum of torques that was up top with the expressions that we found a second ago. I've kept the color coordination. So this torque right here, or this term, came from the torque of NW, the normal force from the wall. This torque, or this term, sorry, came from the torque from the friction force of the wall. One thing that I'm noticing that I'm missing is that I said, and if we look up a little bit, the torque from the normal force from the floor should be negative. So this sign right here should be a negative sign. That term was, this whole term right here, was the torque from the normal force of the floor. And lastly, this torque right here, or this term, again, I keep messing that up, is the friction force from the floor. Okay, so I've got all of these, and what I know is that all of this should equal 0. So I can say, I know that I've got it really scrunched up together, so let's see if I can just make this a little tiny bit smaller so that I can, just a little bit, so that I can fit in my last little bit of equation equals 0. Oh, I ended up losing an L. Here we go, L over 2. Now a couple of really nice things are going to start happening because of some nice symmetry. Number one, I'm going to end up losing all of my L's over 2 because each term has an L over 2 and they should all equal 0. If I divide the left-hand side by L over 2 and I divide the right-hand side by L over 2, it would end up canceling this, canceling this, canceling this, and canceling this. That's really, really nice. So I don't actually need to worry about the distance of my ladder, how long my ladder is. That's the first really nice thing. The next really nice thing is that I can start taking advantage of some geometry / trigonometry things, and I can get rid of this really ugly stuff that's inside of those 2 sine functions. Specifically, the nice thing that I'm going to take advantage of is that sine of 90 plus or minus theta is the same as cosine of theta. So what I'm going to do is I'm going to substitute out anywhere that I see a sine of 90 minus or 90 plus theta, so here and here, those 2 terms, I'm going to replace it with a cosine of theta. And what that does for us is it gets rid of the two terms that are inside of the argument for sine with only one term in a cosine. And that might seem like it's not so good because every other term is a sine, but it's better than having multiple terms inside of my argument. There are other things in trigonometry and geometry that we can take advantage of when I have a mixture of sines and cosines to make everything okay. But unfortunately, there's not a lot that I can do when I have a mixture of single terms in my argument and multiple terms in my argument. So it really does benefit us to switch that out. So I'm going to rewrite this. Again, I'm not going to color coordinate because it's taking a whole lot of effort. Yeah, you know what? I will color coordinate because I can pause the video and you won't even notice. All right, so I've rewritten the equation. I've kept the color coordination, and everywhere that I had a sign of 90 or minus theta, 90 plus or minus theta, I'm sorry, I have replaced it with cosine theta. And what we're noticing is that I have some unknowns. I don't know what these forces are right here. Well, if we scroll up a little bit, we'll remember that we have our sum of forces written out that could help us find some expressions that would be really useful for the forces that we have at the bottom. On top of that, we should remember that there is a really nice equation that's going to help us figure out what the friction is. So I've rewritten my forces down here in the bottom, and on top of that, remember that the angle that we're looking for is the minimum angle. It's the smallest angle it could be. Any smaller than that angle, and this thing is going to slip. Any closer to the ground, it will slip. Well, what would we think the friction force is going to be if I'm just barely holding on? Any more and I will move. If you're thinking the maximum static friction, then yes, you are correct. The friction force, these friction forces are happening at the maximum static friction. What that means is that they have to follow the equation for the maximum static friction. Remember that friction static max equaled the coefficient of static friction times the normal force. So we could combine that with these two forces, and we could say that the friction from the wall will equal the static friction coefficient from the wall times the normal force of the wall. We can also say that the friction force from the floor equals the coefficient of static friction from the floor times the normal force from the floor. Now this is really good for us. This is really, really good for us, because what this does is it rewrites these two terms in terms of normal wall and normal floor, which is good. It will reduce our torque equation from having 1, 2, 3, 4 unknowns to only having 1, 2 unknowns. So let's rewrite it like that next. Okay, so I've rewritten them very quickly. And I've replaced, instead of friction from the wall, I rewrote it as mu static wall times normal from the wall. And instead of friction from the floor, I rewrote it as mu static floor times normal from the floor. So you'll see really quickly that I've reduced my equation from having 4 unknowns to having 2 unknowns. I could actually keep going now, because I could take advantage of this equation right here, and I could rewrite certain other unknowns in terms of something that we've already got. Specifically, what I could do is I could replace the normal from the wall with an expression for the friction from the floor. But we already know what the friction from the floor is. That's going to be this expression over here. So think about it like a double substitution. I could get rid of every normal from the wall variable with a floor variable. So I'm going to rewrite this really quickly and very small. I'm going to just zoom in over here. And I'm going to rewrite this expression as follows. I'm going to say that the friction from the floor equals the normal from the wall. This just came from our sum of forces, and all I did was move this term to the other side of the equal sign. Now I'm going to take advantage of the definition of maximum static friction along with this substitution here for normal from the wall, and I'm going to say that the mu static from the floor times normal from the floor is going to equal normal from the wall. And what I can do is I could substitute this expression right here anywhere that I see a normal from the wall, specifically right here and right here. And what that will do is give us one expression with one unknown, the normal from the floor. So I'm going to rewrite it really quickly. It's going to look like magic to you guys. It's not. It's just physics. Give me 1 second. All right, so I've rewritten our expression and I've substituted in, as you can see right here, I've substituted in mu static from the floor times the normal from the floor everywhere that I saw a normal from the wall. So in these two spots here. Now something really nice is going to happen because every single term is going to have a normal from the floor variable. The first term has it right here. The second term has it here. The third term has it here. The fourth term has it here. So what I can do is I can substitute that term out. I can factor it out. And then, because it has to equal 0, and I know that force can't be 0, I can divide by it and cancel it out. So what that means for us is I can cancel this, cancel this, cancel this, and cancel this. What that means is that the only things left in my equation are the mu's, which I know, and the theta terms, which I'm looking for. And that makes my life really, really nice and easy. Okay, so we're going to start to rewrite this and clean it up a little bit. And I'm going to combine like terms and start factoring things out so that I can isolate my knowns, which are all of my mu's, with my unknowns, which are all of my theta terms. Okay, so let's do that all in purple because as we all know, it's the best color. So I'm just going to rewrite again. The sum of torques is going to equal. All right, the first term here is a sine term, so I'm going to combine that with this term here, which is also a sine term. So I'm going to rewrite that as the mu static from the floor times sine theta plus mu static from the floor So mu static from the floor, sine theta. Okay, so I've taken care of this term and I've taken care of this term. All right, next thing I'm going to notice here I've got a cosine and here I've got a cosine. So I'm going to combine those together. Okay, plus mu static from the wall times mu static from the floor cosine theta minus cosine theta. And this should all equal 0. All right, well, Here in this first section, this first piece here, they both share a sine theta, and actually they both share a mu static from the floor, so this will turn into 2 mu static from the floor sine theta, which is nice. This is pretty sweet for us. On the other side, on this side here, they both share a cosine piece, so I can factor that piece out, and that will look like this. That'll be plus cosine theta outside times, what do I have left? Well, in the first term, I've got mu static from the wall times mu static from the floor, and from this second piece, I get minus 1. If you don't believe me, you can redistribute this cosine piece into each of these, and you'll see that I'll get the same result from the top, and that's going to end up equaling 0. I'm so close. I'm almost there. What I want to do is isolate my theta pieces. The next major thing I'm going to do is move my variables from one side of the equal sign to the other. I'm going to move one of my terms. So I'm going to pick one randomly. I'm going to pick this term here, and I'm going to move it to the other side of the equal sign. So what's that going to look like? Well, I'm going to get 2 mu static from the floor sine theta equals negative cosine theta times mu static from the wall times mu static from the floor minus 1. Okay, I'm really close, guys. The next thing I'm going to do is distribute this negative inside of my parentheses over here, inside of my binomial. The only reason I'm doing that, honestly, is because I want to leave the cosine piece alone so that I can do something with it to get rid of it. It'll make my life much easier not to have a floating negative. That'll be very simple. That'll look like this: 2 mu sine theta, mu static floor, times sine theta equals cosine theta times, if I distribute this negative in, I'm just going to flip this over, 1 minus mu static wall times mu static floor. This will become negative, and this will become positive, and you guys know how much I hate leading negatives, so I just flipped the terms. That's totally fine. Now I'm going to start combining my like terms and my unlike terms. Okay, I'm going to start combining like terms, and get rid of my mix match. On this side, I'm going to divide this by cosine theta. That means I have to divide this side by cosine theta. What that's going to do here is cancel that out, which is good. What that's going to do on the other side is going to let me divide sine by cosine. And this is where we're going to take advantage of a little bit of trigonometry, because I know that sine divided by cosine is tangent. So I can rewrite this as 2 mu static floor tangent of theta. And just like that, I've managed to fix my major problem. The fact that I had sines and cosines made my life really difficult, because if I'm solving for theta, I'm going to need to use an inverse trig function. Unfortunately, I can only use one at a time. So if I had an equation of just sines, I could use inverse sine or arc sine to find the angle. If I had an equation of just cosines, I could use inverse cosine or arc cosine to find the angle. But if I have an equation of a mixture of sines and cosines, I can't use my inverse functions. But now that I've divided by cosine and I've brought them together and I've turned it into tangent, I could use inverse tangent and get an angle. I am missing one more piece though. I do need to divide by 2 mu static floor on both sides so that I have completely isolated my theta variable. So that's going to give me tangent theta equals 1 minus 2, oh, I'm sorry, not 2. I got a little bit ahead of myself. Mu static from the wall, mu static from the floor, divided by 2 mu static from the floor. Now, I'm not done yet. Technically, I'm not done because I'm not looking for tangent theta. What I'm looking for is just theta. So what I'm going to do is take tangent inverse of tangent theta. And what I do to one side, I must do to the other. So that means I have to take tangent inverse of 1 minus mu static wall times mu static floor divided by 2 mu static floor. The nice thing is that all of these terms in here are numbers. They gave us those numbers. We know that mu static wall is 0.3 and mu static floor is 0.4. So I could substitute in there and figure out the number. What happens over here to the left-hand side? Well, tangent inverse of tangent, these things end up canceling out. And what that leaves me with is an expression for theta, the angle, which is what I'm looking for. Theta is tangent inverse of 1 minus mu static wall times mu static floor all over 2 mu static floor. And if I go to my calculator and I plug these all in, and I'm in degrees, not in radians, I'm in degree mode, I'll be able to find an answer. And that answer would be 48 degrees. That would be my answer. Notice that I didn't need a whole lot of variables. I didn't actually find out what the magnitudes of my forces were. I didn't actually need the mass of my ladder. I also actually didn't need the length of my ladder. All of those variables ended up canceling out. I just did some tricky substitutions with trigonometry, with a little bit of geometry, and some really nice substitutions with my sum of forces. Now, I know that I said there was going to be a second part to this video where we would do the same thing but using the line of action instead of using some tricky signs and angles. And noticing that this video is already very long, I think I'm going to save that for a second video that I'm going to work on later and send your way. What I would recommend that you do is try to do it with the line of actions yourself and see if you're right when I put up the second video of this.